Hello and welcome to Lecture 9 for ECE 205. This lecture is all about boundary value problems, and there's not much regarding boundary value problems in the text, so I'll give you my slides as your primary resource for this topic. Okay, so what's a boundary value problem? Where do they arise? How do I solve them? All those good type questions. Well, let's just start with a very concrete example. Suppose you're trying to impress your friends by tossing a ball into a cup across the room. So if you want a little diagram, we could say that you are maybe standing over here at some initial height, and my drawing is atrocious, but yeah, here's your ball, and here's the cup over here. Okay, so for the purposes of this, we're ultimately going to assume that the cup is defined by a particular point. So let's just call, say, this point in the middle of this cup the point x sub b, comma, y sub b. Okay, it could be higher than you, lower than you, whatever. And we'll call the initial point that you have the ball at, we'll simply call this thing here the point 0, comma, h naught, where 0 is kind of our reference frame and height is taken from some height down here, doesn't matter where. Okay, your goal is to get this ball to fly through the air and land here. Okay, so now that you've taken ECE 205, you think, hey, I could model this, the property of this ball flying through the air by a differential equation, and then I could try to solve my initial value problem such that I don't overshoot by, say, throwing the ball over here and landing over here, which is bad, or I don't undershoot, right? I could describe this as an initial value problem. So let's look at that initial value problem and kind of go from there. So here, again, instead of blindly trusting and guessing at the appropriate angle and velocity, we instead try to math this out using what we have from 205. Okay, so the motion of the ball is given by these governing equations for the y position. So here I'm simply saying the acceleration of the ball is given by gravity. Notice here, with this assumption, I'm implicitly assuming that there's no drag or anything on the ball. See a question on A1 there. And then I'm assuming that my initial height is given by this height h0. So that's kind of my initial point here. And this initial direction that I throw the ball in, this thing here, that velocity, the speed of this, or the length of that vector, I'm assuming is just going to be this v0 times sine of theta, where theta is going to be this thing here. So theta is just this angle between that and kind of the flat line there. Okay, so pretty standard stuff there. Just the initial velocity is what I put into the ball into the upward direction, and the initial height is this. For x, we assume, again neglecting friction, that there is no acceleration kind of pushing it or pulling it in the x direction. Kind of also we're assuming there's no like breeze in the air or anything like that implicitly in this differential equation. And I'm assuming my initial position is at 0. Again, that's just by choice. I can always define where my point here, where my point 0, 0 is at. So yep, I can just do that by choice. And here the the x component to my velocity, our initial velocity, would simply be this thing here, where again, that's the velocity that goes purely in this direction here. Okay, so if you tie that together, the Pythagorean theorem, I simply get that the original velocity would just be this v0 term. Okay, so that's the governing equations that model this. And here, just for completion, we're noticing that the position of the ball at time t would simply be given by this ordered pair evaluated at t. This angle theta is, again, the angle that you throw the ball at. This h0 is the initial height, and this v0 is the velocity of the ball originally. Okay, so we know how to solve these various initial value problems, the first one and the second one here. In fact, solving something similar to this is one of your homework assignments. But once we get the solutions to this initial value problem, we need to know what it means for us to succeed in impressing our friends within this context. Well, it means that eventually the position of the ball is exactly in the cup. So mathematically speaking, we could say, hey, if there is some time tf such that the position of the ball, this thing, is equal to that point in space, then we impress our friends, right? That's what we want to do within this context. And here, what we personally are in control of are these initial values here, right? I get to pick H naught if I move my hand up or down. I technically could pick the starting point 0 if I move my hand left or right. And I get to pick the original initial velocity and the angle upon which I throw the ball, right? So really, we control the initial conditions. And our goal is to pick the parameters such that the solution, namely this thing here, to the initial value problem, well, problems, satisfy this condition here for some TF in R. Okay, so in practice at this point, I could solve these, get some expressions that depend on my initial condition, and then set that expression that I get equal to this single point here, and try to solve for the time upon which I actually hit the basket, and the angle and the velocity. Okay, so I could do it this way, but instead, there's another way that I can phrase this problem. So instead of guessing the initial conditions, I can phrase this as a boundary value problem. Note, within this context, these are actually equivalent mathematical questions, but I can rephrase this as, well, here, instead of saying I have this initial velocity that I want to pick, I can say, hey, I want at some time TF, where you can pick the time, potentially, for the ball to be in the Y position, Y sub B, which corresponds to being in this basket, right? And similarly, I want X to be able to satisfy this system here, where at the same time T sub F, the position of the ball is X sub B. So really, instead of deciding that arrow, I'm really saying, hey, I start at the green spot. So my starting point's here, my ending point is here, solve that differential equation. So take the equations of motion and try to satisfy these two conditions simultaneously. That's basically what we would be doing if we solved this initial value problem and then tried to pick the initial value such that we matched. Okay, so if we can solve this thing here, then we have a solution, and also if we could solve this thing, we have a solution. The two are equivalent here. Okay, so let's just turn this into an example. If possible, solve the boundary value problem. First equation, second equation. So why do I say if possible? Well, in general, if I just give you an arbitrary boundary value problem, you can't necessarily solve it. But in this case, you're actually kind of guaranteed a solution, since we know solutions to this can be chosen such that the position, say, y of t and x of t for any value of t can be any real number, right? So it's a property we haven't proven, but it is true for this case. Okay, so let's try to solve this. So one method that you might immediately go to is, hey, I could convert the boundary value problem to an initial value problem, namely this thing here, and then I can solve the initial value problem because I already know how to do that, and then try to find this value of TF and this value of Y sub B or X sub B. So you can do that, and that method where you take a boundary value problem and turn it into kind of an initial value problem where you guess about what the velocity is called a shooting method. So generally speaking, if you're numerically solving boundary value problems, you do that method where you turn it into, just clear that out, a initial value problem, and you kind of shoot, and you go, oh, I overshot, pick a lower velocity, oh, I undershot, use the fact that the solution is continuous in terms of parameters, along with the intermediate value theorem, to know that there's going to be some middle velocity such that you do actually hit the basket, and just kind of keep guessing back and forth. And yeah, that method does work. But instead here, let's try to solve this boundary value problem directly on first principles. Okay, so here I have two kind of separate problems from each other, so let's just kind of solve them one at a time. So if I label these, say 1 and 2, so I can say to solve equation 1, we simply need to integrate this thing with respect to t twice. So we can just say we integrate to c in here once I integrate this twice. And yes, this is giving away part of a solution for one of the homework questions. So if you are paying attention and watching the lectures, you kind of get that for free. But here I'm going to have two arbitrary parameters that I don't know. So let's just call it a naught t plus my other parameter A1. Okay, so in your homework, you do need to kind of show the details of why this works, but that's what you'll get for this solution. And here, we want this thing to satisfy these conditions. So applying the boundary condition, well, what does this give me? Well, here my y of 0 is equal to h naught. Well, if I plug in, oops, I don't put that there. If I plug in 0, I simply get a1 has to be equal to h naught. So I know what a1 is. So next, my y of tf. So here I don't know what tf is, but it's just given to me as the time upon which you want the ball to hit the basket. So that needs to be equal to this. And if I plug that in here, I simply get this expression. And this whole thing simply needs to be equal to this y sub b. Okay. So I now need to find my coefficients that satisfy these. So I can say or thus if you want. Let's do that. So from the first equation, I get a1 is equal to h naught. And from the second equation, here if I wanted to solve this for a naught, I would get a naught is equal to, so in this case I'd have yb minus, I have to pull this term over, and I can just replace it with the h naught. I have to pull this over, so a plus g all over 2 t sub f squared. And this will all be over my t sub f. So here I'm assuming my t sub f has to be non-zero to divide by this. And physically, within the context of this problem, if tf was 0, then there's no way I can satisfy those boundary conditions because I can't be in two places at the same time unless I start with the ball being in the basket, and that's not going to impress anyone. Okay, so from here I can kind of simplify this out just by cleaning up the 2. So I could simply rewrite this whole thing as my y sub b multiplied by 2 minus 2h naught plus g tf squared all divided by 2tf. Okay, so this is what I need my coefficient here to be for y, or for this term here, and this is what I need my coefficient to be for a sub 1. Okay, so I need to satisfy this thing here. So next up, I want to solve 2. So 2, I basically do the same thing. So basically, I could say for 2, what do we find? Well, when I integrate this expression for x double prime, I'm simply going to get x is equal to, say, b1x plus b2. Okay, so now the boundary conditions, what would that give me? Well, my boundary conditions for x, the original one, was that x of 0 was equal to 0. And again, this is just my choice, right? I could pick my initial point to be whatever I wanted to. That's a choice of coordinate systems here. So if I plug this in, that tells me that b2 has to be equal to 0, right? Pretty straightforward. For the second one, I want b of tf to be equal to b x of b. So here, my x of tf, that needs to be x of b. So here, if I just chase this out, I simply get b1, here my tf. And I'm just going to automatically put this plus 0 because I already know what b2 is. This needs to be equal to x of b. So from here, that tells me that my b1 needs to be equal to x of b over t sub f. Okay, so I did manage to solve the boundary value problem. So putting this together, I can say, thus, the position of the ball at time t is, or more precisely, needs to be within the context of kind of the bigger problem. But in terms of this system of equations, it is. Well, what is this going to be? Well, it's going to be some points x sub t, comma y sub t. And this will simply be given to by, well, for my x, I simply have b1 x2 plus b2. b2 is 0. So here I can simply replace this with x sub b divided by tf times x. Okay, so that's pretty trivial. And here I noticed I made a oopsie. This x should be a t, so let's clean that up. Okay, there, that's better. And for the y coordinate, I just need to kind of unpack this thing. So it's simply going to be this, where I have these coefficients. So just to save you time, I'm just going to throw that in off camera. Okay, so here I have a solution to the boundary value problem, and kind of pretty clearly, I can make the basket given that the time upon which I want my ball to go into the basket is not equal to 0, right? And again, that's just from a physical perspective. You can't have TF is equal to 0 for the problem to make sense, right? Okay, so finally, this is kind of the end of what we actually wanted to prove for the question. I've now solved the boundary value problem, so I've set out to do what I wanted to. But let's kind of interpret this in terms of what the velocities need to be. Okay, so my initial velocity, the thing that I have control of, was simply this x prime of 0 and y prime of 0, right? That's the thing that I really wanted to know, to be able to know how do I hit it? How do I throw it such that it hits the basket? Well, direct computations give, if I just take this derivative with respect to t, I just get xb over tf. So that is what my v0 cosine of theta needs to be equal to for me to be able to make the shot. And then here, if I take its derivative and set t equal to 0, this term vanishes from t going to 0, and this term vanishes from the derivative, so I simply get this term here. So just writing that off camera, this thing needs to be v0 sine of theta. So basically, here I have two unknowns and two angles theta. I could build a system of equations and try to solve that. It's not linear, right? It's a nonlinear system of equations. But from here, you could just do some trig and some algebra to find what v0 and cosine theta need to be if there are solutions there, right? But in either case, this is what the velocity needs to be in my initial value problem in order to hit that point, okay? So this is where kind of a natural way where boundary value problems pop up in nature. So just, yeah, they're very prevalent, and sometimes you can turn them into initial value problems instead and solve those. Okay, so let's go on. Okay, so in slide form, again, all squished, click here to see the full res version, which will be the thing that I had on the previous screen, all that good stuff. Okay, so now let's look at a different problem. If possible, solve this boundary value problem. Okay, so like before, the first thing I'll do is try to find the general solution to the differential equation. In this case, that's pretty trivially. We can just say note that y is simply going to be the integral of sine of x dx. And the integral of sine of x, what's that? Well, that's just negative cos. So here I'll get a negative cosine of x plus some arbitrary constant. Okay, so this is pretty trivial, so I can just say, note, this solves the d. Okay, pretty straightforward there. So now I go to apply the initial condition. So y of 0 is equal to 0. This thing tells me what? Well, 0 would need to be equal to negative cosine of 0 plus c. So cosine of 0 is 1. So here I simply get c has to be equal to 1. Okay? So now, if I take this, plug it into here, and try to solve for y of 1 is equal to 2, what do I get in this case? Well, here I would get 2 has to be equal to negative cosine of 1 plus 1. This is not true. Since this thing is not true, then this means there can't be a solution, right? So I can satisfy one of the initial conditions, but not the other. So I can say, thus, there is no solution. Okay, so sometimes boundary value problems, even boundary value problems for first-order linear differential equations, won't have a solution. So now let's just think about this question in another way. I could have told you beforehand that this boundary value problem, the probability of it having a solution, was 0 to start from. Doesn't mean it can't happen again from ECE 108, but if I just consider this here, this thing is a initial value problem. In particular, it's a first order initial value problem where everything's nice and linear. We know that has a unique solution, right? So there is some solution y sub s of x for this equation here, and it's unique. Thus, unless it so happens to be the case that ys of 1 is equal to 2, then it's not going to, or the boundary value problem will not have a solution, right? So here, you really need this 2 to be equal to ys of 1, where ys is a solution to that, for this question to have a solution, okay? So it is not possible to solve this boundary value problem. Okay, so here will be our solution in slide form, and again, you can click here to see it. But this does not have a solution because of that. Well, we can't satisfy the two boundary conditions at once. Okay, so now let's look at one more example that's a little bit more involved. One, for what values of L does this boundary value problem have a solution? So we know this could be feasible to be able to find solutions like this if I could pick L. So it's a natural question I could ask. Further, I can ask what values of L does it have no solution? And finally, if we replace the second boundary condition with y of pi is equal to -1, what are the solutions? Well, let's tackle these one at a time. So step 1, what we're going to do is we're going to solve the differential equation y double prime plus y is equal to 0 to find the general solution, and then we'll start applying these conditions. Okay, so here the characteristic polynomial, would simply be what? Well, r squared plus 1. So we want to find roots to r squared plus 1 is equal to 0. Well, this has two roots. R is equal to plus or minus I. Okay, so from here we know that the solution, say y sub s of t, this thing is going to have the form c1, say sine of t, plus c2 cosine of t. Okay, so we have the general solution to this homogeneous first-order linear differential equation with constant coefficients. So now I want to ask the first question, when does this boundary value problem have a solution? So we can kind of do a little sub-step here, and if we call this question A, this question B, and this question C. So for part A, what we would do is we'd simply say, hey, I want y of 0 to be equal to 0. So if I apply this here, I would get 0 is equal to, well, sine of 0 is 0. So I'll get 0 plus cosine of 0 is 1, so C2. So from this first condition, this would tell me that C2 better be 0. Okay, so now I have the second condition to apply. So here I would need y of L to be exactly equal to 0. So if I apply this condition here, and using the fact that I already know C2 is 0, I would simply get 0 would need to be equal to C1 sine of L. Now, so tweaking my problem statement a little bit, so it problem actually does what I want it to do, we're now looking for non-trivial solutions. So here, if this thing is 0, then since we're doing arithmetic in the real numbers, this tells me this or sine of L is equal to 0. Okay, so here, since I now want non-trivial solutions, we can say we can't have, or for non-trivial solutions, we have that C1 cannot be equal to 0. Thus, we need to have that sine of L is equal to 0. Okay, so sine of L, when is that 0? Well, sine of 0 is 0, and sine of pi is 0, and sine of negative pi is 0, etc. So this implies that L has to be in pi for some in the integers. Okay, so thus we can conclude this proof by saying, therefore, the boundary value problem has a solution if and only if L is equal to n pi, non-trivial solution. Okay, so for this case, there always is a solution, right? But there's going to be this non-trivial solution only in this case. And in particular for this case, our solutions now would be y of st comma c, such that this is just going to be c sine of t, right? This sine term goes to 0, so c can be any arbitrary parameter. So thus, I really am having an infinite family of solutions, like so. Okay, so that's kind of interesting. In this case, we have infinitely many solutions. Okay, and it turns out we've actually answered part B here. When does this have no non-trivial solutions? Well, for B, from our previous work, we know that we need C1 of 0, or C1 to be 0, or the sine of L to be 0. So we can say we have infinitely many, or we have no solutions when this L that I just found is not equal to n pi for some integer n. So in this case, since we still have the non-trivial solution, since that trivially satisfies the boundary conditions and the function here, in this case, I can say we have a unique solution. Okay, so far in our analysis, we kind of noticed that it's really this choice of L, whether or not L is a good number, where good is kind of defined as getting these non-trivial solutions, then we either have infinitely many solutions or we have a single solution. So next, let's see what happens if I replace this boundary condition up here with this new boundary condition. So notice, by replacing this boundary condition, I'm throwing away the possibility of having a non-trivial solution, right? Because it can't satisfy the boundary conditions. Further, here my choice of pi is a very particular choice, and you will see why. Okay, so here I would basically, going through the same process as what I did above for parts A and B, I would apply the first boundary condition, and I would get this thing here, right? So my starting point would be that something like from the above, this thing solves this. In particular, this is the unique solution to this factor here, just because the method that we used actually grabs all the solutions. Okay, so now we want to apply the other boundary condition. So in this case, I want to say, hey, y of pi needs to be equal to -1. What does this thing imply? Well, this means -1 has to be equal to c times sine of pi. Uh-oh, that is 0. This is a contradiction. Okay, so from here we can say, thus, there is no solution in this case. Okay, so just kind of tying this together a bit, let's just do a thought experiment. If instead of pi, or in pi where n is an integer, if this is any other number, then the sine term would be non-zero, and I could divide by it to solve for c. So in here, I kind of have two cases. If the point that I'm picking here for my L is not an integer multiple of pi, then there is a unique solution where I just divide through by the sine of L, and if it is an integer multiple of pi, there is no solution. So in this case, we'll just say there is no solution and box that in. So here, this is our big thing here. Okay, so you can see just from analyzing this case that there's kind of three things that can happen, at least in this case. One, I could have infinitely many solutions, and of those infinitely many solutions, I'm going to pick up the non-trivial solution. Or I could have a unique solution, or I could have no solution. It turns out that for differential equations of this form, or in particular linear second-order differential equations with constant coefficients, the corresponding boundary value problems will fit in one of these three cases. So let's make that a theorem. Okay, so just going back to the slides, again, here's this. You will have the ability to go to a link to grab the solutions. And here it's god-awful because I didn't put any attention to the aspect ratio because I expect you just to go to there. So it's kind of written like I would want to see in a homework solution. Okay, so check that out, not the slides here. And let's look at a theorem. Consider this boundary value problem here, where again, a, b, c are real numbers, and we're assuming a is non-zero. And now if the roots r plus minus to the characteristic are real, then we're going to have a unique solution for every L that's not equal to 0, and for every y naught and y1 and r, right? So if L is 0, kind of bad problems here. Definitely not going to get a unique solution, and probably not going to get a solution statistically, like y1 needs to be y0 there, right? Okay, so next up, if we have complex pairs, then we have a bunch of different possibilities, as we've just seen. So in general, what we just saw will be true. There's either going to be a unique solution, so kind of like this case that we had right here, where there was only one solution to it, or the cases over here if L was not a multiple of integer multiple of pi. Or there's going to be no solution, like we found down here in this case, or there's going to be infinitely many solutions, like we found up here. Okay, so I'm not going to prove this, but let's just think of why this would be true. Well, we know from previous work that this thing will emit a general solution, and we know the functional form of that solution based off of whether or not the roots are real or complex pairs, or if I have a repeated root, right? So in the case where they're real, I either have two solutions of the form e to the r plus x and e to the r minus x in my general solution. So in that case, I could simply set up a system of linear equations by plugging in the initial conditions, and you can show pretty easily that you can always find solutions there. In the other case where I have two real roots that aren't repeated, that are repeated, then I have e to the rx and e to the rx times x, right? And in those cases, you can also show that there's a unique solution here. So that's why I have a unique solution in this case. But if I have complex pairs, then depending on what L and Y are, you'll be in these various scenarios here, as you've seen from our one previous example. Okay, so I'm not going to prove this, but it's not bad to prove at all. And it is something that I could ask on like a midterm type thing or final type thing, if it were to be maybe open book. Because here there's kind of a lot of moving parts that are sitting here. So I'd kind of want to give you open bookness so you could see some of the theorems of how other things worked here. I mean, I could give it as a closed book thing, but it would be a really hard closed book question, just for a metric of what type of questions you could expect. Okay, so now we get to the fun stuff. Boundary value problems from partial differential equations. So far in this class, we have not talked about PDEs at all, and this is kind of purely because before you can even think of tackling PDEs, you need to be able to solve ODEs. Okay, so let's change this and talk about PDEs a little bit. So the vibrations of a string of length L with constant elasticity C, I have quotes around elasticity because I'm lying to you here, but constant something that's related to elasticity and density and the Young's modulus, that type of stuff. Okay, that has its edges clamped at 2 points is described by this thing here. So the partial differential equation is just 2 derivatives of t is c squared 2 derivatives of x. The initial conditions are that initially the string has some position, and initially the string has some velocity. And then boundary conditions are these two here for the clamped. So let's actually just take a step back and look at this question to physically see what I'm talking about here. Okay, so let's just draw in a string. So here I have kind of my bar sitting something like this. Here I have my lengths. So on one edge over here, we'll say that this is at the point x is equal to 0, and this point over here will be at x is equal to L. So clearly this has length L. Okay, so here this is the differential equation that I'm saying models this whole thing basically inside the interior of this domain. So really you could, if you want, say x is in this open interval, because at the edges we've kind of defined what's happening. And then beyond this, I'm saying that this initial condition here is telling me that the string originally has some position, right? I kind of plucked the string, maybe something like that, or maybe I'm holding the string up by like a tiny little point here. So maybe it looks something like that. But there's some initial position. In addition to this, I'm assuming that the string has some initial velocity, right? So the string could be going, say, up or down at any given point, or in the case where I'm physically just holding this up, the initial velocity would be g of x is equal to 0, okay? So this is kind of a physical setup describing a string turned into a mathematical construct, right? So different things I could do is I could change these boundary conditions, like, hey, what if the string is being held up over here? Then I have something that looks like this, where I replace this 0 with some constant. And there's lots of other things we can do, and I'll talk briefly about other boundary conditions at kind of the last slide of this lecture. Okay, so if this describes a string, which this describes quite a few strings, at least in an idealized framework, then if I want to know how the string is going to move, I need to be able to solve this partial differential equation. Now, we won't actually have the tools to solve this in all its glory until the second half of the course, but with boundary value problems now in play, we can actually make some progress towards trying to find a solution. So let's see how this happens. So the first thing is, well, I have this differential equation, I really want to solve it. A natural way of doing that is to make an ansatz, right? So we've noticed before, making an ansatz to solve various ODEs worked really well. Let's try it here. What ansatz should I make? Well, it turns out that the whole thing of separability we talked about earlier in the course has a direct application to partial differential equations. So we're going to assume that the PDE has a separable solution u of the form, well, u of x comma t will simply be some function of x times some function of t. Okay, again, this is an assumption. It might not work, it might not give me a solution, and generally speaking, for most partial differential equations in the wild, you're not going to find a solution of this form. It does work for this, and we'll see kind of a little bit of it why now, and the rest of why when we start doing Fourier series stuff. But if I plug this into the PDE, then differentiating it simply gives me this thing here, right? So here UTT, I get the derivatives attached here, and here UXX, I get the derivatives attached over here. Okay, so now that I have a form of the PDE of this form, what do I want to do? Well, previously when I worked with separable ODEs, I could just integrate both sides and I was done. I can't do that here, right? Because the derivatives on this side are a function of time, and the derivatives of functions on this time are a function of x. So if I chose to try to integrate with respect to time, I could simplify this term over here a little bit, but over here I still have complicated stuff, right? The integral of t, I can't really do anything. So the natural thing to do is to divide the whole thing through by x times time to finish separating out the variables. So if I do that, dividing by c squared tx, c squared is just for convenience, you don't have to, but it's traditional. So if I divide by that, then I simply get this thing here. So now I have an equation where I've separated my variables out fully. And do note here, I do have to assume that these x and t's are non-trivial to be able to do this. Okay, so now I still have a problem. If I integrate this thing with respect to t to simplify things out a bit, then I have to integrate this with respect to t, which just adds an arbitrary t there. It doesn't really help me. You can try going along those lines, but it won't work. So instead, we have to notice something that is a little bit clever to see. But this thing here, the left-hand side, does not depend on x. It only is a function of time. And the right-hand side does not depend on t. It is only a function of x. But they are equal. So what is this really telling me? Here, it means that my differential equation is something that looks of the form some big function of t is equal to some big function of x. So now, since this is true, then since this doesn't depend on x, that means this function can't actually depend on x as well, because if it did, then this equality can't hold. Now, since this is also true and this doesn't depend on t, that means this can also not depend on t. So since these two things are equal, they must be some constant. This is a key idea here, okay? So just unpacking this out, they must be some constant, and traditionally you call it negative lambda squared. I'm just going to start with negative lambda, dropping the squared because you'll see why you want it to be squared, but I don't want to put those extra assumptions in here for now, but I'm leaving the negative just because it makes things a lot more convenient and it doesn't reduce the scope of things here. Okay, so from here, the partial differential equation now becomes two eigenvalue problems. this thing has to be negative lambda, and this thing has to be negative lambda. So explicitly, my eigenvalue problems that I need to solve are going to be this thing and this thing, where I simply set this whole expression here equal to lambda, and then simply multiplied by x for this equation and c times t for this equation. So I had a typo originally, it should be this. Okay, so now instead of solving the partial differential equation, I can replace it with these two equations. Okay, all good. I can solve this for t, we know how to do that. I can solve this for x, we know how to do that. I don't know what lambda is, that could be a problem, but we'll address that later. Okay, so now I still need to apply the initial conditions and the boundary conditions, but I kind of have a functional form for my function u, so let's just plug this in and see what the initial conditions and the boundary conditions simplify to. Okay, so pretty direct comparison plugging it in. If I do the initial conditions, I would plug this in and I get t of 0 for both cases. Well, t of 0 here and t prime of 0. So the initial condition, the first one would become this, and the second one would simply become this. Okay, I don't know what t of 0 is, and if t of 0 and t prime of 0 are 0, that could be problematic, since things would cancel and I couldn't actually do stuff, but we will address this later in the course. And for the boundary value, or the boundary conditions, I would simply get this term here and this term here. Okay, so this again could be an issue, but only if I was unable to get either of these quantities to be 0 identically. Okay, so now I could go through here and note that, hey, sometimes the trivial solution would work, but in general, that's not going to work because these f and g functions are not necessarily going to be 0 or, yeah. So what I'm going to do at this point is I'm going to assume that my solution is non-trivial, and if I do that, I can simplify the boundary conditions. Why? Well, if this thing is non-trivial, I can divide by it and just get x of 0 is equal to 0, or alternatively, you could think of it as, hey, if this is non-trivial, that means it's not 0 for all values of time. Therefore, if I want to try to solve this such that I satisfy these boundary conditions, I need to have that this x of 0 and x of L are equal to 0. Okay, so quite a bit to swallow, but let's just take a step back and see what we've now done. Okay, so we've turned our partial differential equation into these two eigenvalue problems, and we turned our initial conditions into something that's still kind of messy. We're not going to work with it now, we'll deal with it later. And we turned our boundary conditions into something particularly nice. Okay, so from here, for x, we can simply find x by solving a boundary value problem such that x solves this eigenvalue problem, and x satisfies these two boundaries conditions. Okay, so that would be how to deal with x, and the natural question is, well, how do I deal with t? I have that PDE I can solve, ODE that I can solve, but then I have these conditions here. Well, just as a side note for now, to solve for t, I first need to solve this differential equation, and then I need to somehow satisfy both of these conditions simultaneously. Now, if f of x is just coming from solutions to this boundary value problem itself, you might think, hey, there's no way I can possibly satisfy these boundary conditions here. Like, f of x and g of x are arbitrary functions. X of x could be one particular solution if the boundary value problem has a unique solution, or it could be like an infinite family of solutions. So how can I do this? Like, how is that possible? Well, more on that later in the course. I'll leave that as an open question to try to motivate the second half of the course. So at some point, we're going to come back to this question, and we are going to solve this for t, and you'll see how that works then. Also, you'll see why I'm not covering it now. Okay, so for now, we can tackle this problem, right? We've solved boundary value problems, a couple of them. This one doesn't look particularly difficult, so let's solve this boundary value problem. So there, and we're going to leave the rest of the problem, namely solving for t, for after the midterm. So let's just kind of take an look at this and see what we can do. Okay, need to solve this. I don't know what lambda is, but at the end of the day, by the time I'm done with this, I will know what lambda has to be. Okay, so here, let's just focus on the PDE. So if I have x double prime plus lambda x is equal to 0, the characteristic polynomial for this would just be this thing here. It's going to be my p of r is going to be r squared plus lambda. Okay, so the roots of this implies that the roots are just going to be r is equal to plus or minus the square root of negative lambda. Okay, so I don't know if lambda is positive or negative at this point, so I have different cases I need to consider. Okay, so let's do that now. So case 1, if lambda is less than 0. So in this case, it turns out that there are going to be no non-trivial solutions, and I'm going to leave this to you as an exercise just because lack of time here, and it's not too bad, right? If we have these two roots, you just write out what the general solution to this looks like, apply the boundary conditions, and show that the only solution is the trivial solution. Okay, so now in case 2, if lambda is equal to 0, we get that the only solution would simply be x is equal to a plus b t, and under that we also get no non-trivial solutions. So I'll leave that as another exercise. And now we only have one case left, case 3, if lambda is greater than 0. Okay, here's where all the interesting things happen. And we're going to start by making an observation that makes everything else that follows a lot easier. So since lambda is greater than 0, I can introduce a new constant, and I'll say we're going to let lambda be mu squared, where here this mu is just some real number, okay? So since lambda is greater than 0, I can always do this, and it turns out that this makes things a little bit cleaner. So with this thing here, I get that r is simply going to be equal to plus or minus I, the square root of negative 1 sitting there, times the square root of mu squared, so simply I mu. Okay, so those are my roots. Okay, so now if I can solve mu, then I just square it and I get lambda, right? So let's just go through this and see what the solutions would look like. Well, we know what they are, right? The solutions will be x of x, and they're going to be of the form of a sum of sines and cosines. So c1 cosine of my mu times x plus a c2 sine of mu x, right? So we solved this problem a lot. We know what the solutions look like. So now we want to apply the boundary conditions to this. And our goal for doing this is to find out what these coefficients need to be, and or to maybe find what mu is, because I still don't know what lambda is. It's unknown. Okay, so what I'm going to do for the first one is just x of 0. What happens here? Well, if I plug in 0, the cosine term goes to 1, so I get this, and that's going to be, plus a term of 0 here. Okay, and that needs to be 0 because of the boundary conditions. Okay, so from here, this directly implies that c1 has to be 0. Okay, now I have one more boundary condition to apply. Okay, so just cleaning that up a bit here. So for the other boundary condition, we have that it needs to be the case that x of L has to be 0. Okay, so let's see what this tells us. Well, c1 is 0, so this tells me c2 times sine of mu times L has to be 0. Okay, we've seen something similar to this before, but instead of having this mu term here, we just had the L, which was a fixed constant. So we want non-trivial solutions, right? If we have non-trivial conditions, then we have issues with satisfying the initial conditions, right? Because if x was just 0, then that means up here I just get that the function u is just 0, and it can't satisfy these conditions unless they're trivial as well, right? So here I thus have to say that c2 cannot be equal to 0. Okay, if it's 0, I'm kind of done and I haven't found a non-trivial solution. So from here we can say thus, I need the sine of mu L to be 0. But L is a physical parameter. It was given to me. like Fred gave it to me, whoever gave it to me. So I'm kind of stuck with L, but mu is lambda, and I don't know, or mu squared is lambda, and lambda was a free parameter, right? I didn't know what it is. So I can solve this for mu. So if I do that, well, pretty clearly, the first thing is that mu L needs to be equal to n pi, where n is just going to be some integer. We saw that earlier. And here, if I divide by L, I get mu needs to be n pi over L, where n is an integer. Okay, so now if I take this and use the fact that my lambda is mu squared, this tells me that lambda has to be equal to n squared pi squared over L, where n is any integer. So in here we kind of can restrict this a little bit further. We know the lambda has to be greater than 0, so we can say n is going to be an element of the natural numbers. Okay, so we found values of lambda that work, namely this thing here, but we've also found a solution to the boundary value problem if we put all this together. So from here, we know that I have solutions of this form where the condition was that C1 was 0, so the cosine term goes away, but the sine term is anything it wants to be, right? So thus, I have x of x now as a function of lambda is simply also as a function of c if you want. This is equal to arbitrary constant times sine of, so here if I just go back up here, it was originally this mu x, and lambda squared, or sorry, mu squared is equal to lambda. So here I want to take the square root, and without loss of generality, I can take the positive root, because the constant can absorb the negative that the sign would output. So from here, I'd simply get this of the square root of lambda x. And now I can further clean this up by getting rid of lambda and then just say x on its own as just a function of x in and c would simply be equal to some constant sine of, well, just take the square root of this thing, so n pi x over L. Okay, and here n is again going to be an element of the natural numbers. So this is my solution to the boundary value problem. Now let's go one step further and look at what these things look like. Okay, so it's not required for this problem, but yeah. So the C, like if you just scale it, it just scales the amplitude, so that's not particularly interesting. But if I just look at, say, x of x, comma 1, and C doesn't matter here. So instead of using that notation, I'm going to use this notation here, x in of x. This thing would simply be sine of pi x over L, right? And now what does this thing look like? Well, this looks like here, if this is my 0 and this is my L, this is just a hump that starts at 0, goes up, and then goes down to here. So if I plug in different values of C, I'll get different curves that look like this, just sinusoidal curves, okay? So now if I plug in x1 of, or sorry, x2 of x, this would simply be the same thing, but with 2 pi, right? Okay, and if I visualized this, this thing would have a 0 at L over 2. So if this is 0, and oops, let's go down here. So if this mark is 0, that is L over 2, and this mark is L, then this function would go up and down, and then the other way up and down, okay? So if you kind of notice, if I keep going up higher and higher, I would get more and more of these oscillations. So say up into the kth case here, in this case, I would have k oscillations, and the widths of these little intervals upon which I have this like half of sine sitting would be L over k. So I'd have one oscillation up to L over K, another one by the time I go from L over K to 2L over K, etc., and K of them as I go all the way up to N. These oscillations, these structures here, are called eigenfunctions, right? Because I'm solving an eigenvalue problem originally up here, and these values of lambda are called the spectral frequencies, okay? So we would say, using higher nomenclature, that the spectrum of this operator, that the spectrum of this thing, would be all the values of k. So the spectrum would just be all the natural number multiples of this squared of this pi squared over L thing. Okay, so we have infinitely many of these solutions, and it turns out that because I have these particular solutions, I can actually solve this unknown bit here that we've left out for how to solve for t. Okay, so we need Fourier series for that, so we can't do it now, but we will do it. Okay, so TLDR, we set up the equation, we set up the characteristic polynomial. We considered two cases where there were no solutions. We considered this third case where we found that by applying the boundary conditions, so applying these two things, we found that our non-trivial solutions only happened when this value of lambda took on very particular values, in this case, values of here. Okay, this is similar to what we saw in that previous example, to be explicit. In this example here, where L has to take on certain values to be able to have these non-trivial solutions. Okay, so this, which again, this is absolutely atrocious because of the aspect ratio, so definitely check out the full resolution version that I'll upload. This is one application of a boundary value problem that appears all over when trying to solve PDEs. Generally speaking, when you try to analytically solve a PDE, you first have to solve a boundary value problem. Okay, so I'll end with kind of a very TLDR of different types of boundaries you can consider. So we've already considered Dirichlet boundaries, where the function is some constant at the boundary. Next up, there's Neumann boundaries, where you say that the derivative of the function is constant. So what does a Neumann boundary really tell me? Well, if I have some blob like this, then if I take the derivative normal to the blob, so going this way, if this is some constant, then that's actually telling me if stuff is going inside or outside of the blob. For instance, if this was a circle that was completely insulated and nothing could go through the circle, then the boundary condition would simply be that dy dx is equal to 0 along this boundary. Okay, that's where those are physically useful. Next, there's Robin conditions, where you kind of have a mixture of these. And again, these appear in lots of different cases if you have like certain advection at the boundaries. And then there's mixed conditions, say like if one half was clamped but the other side was allowed to move. For instance, say if I had something like this where, let's say the stuff on the orange half was insulated, but the stuff on the other half wasn't insulated, then on one half we would want a Dirichlet condition potentially, and the other half where it's insulated you want the Neumann condition, with C1 being 0. And finally, there's the Cauchy problem, or Cauchy conditions, where you apply two boundary conditions at one point in time, or along the boundary, and these ones, generally speaking, have kind of more issues with having a solution, but these are very important for problems such as a dam break problem. So you have a dam that's holding back water, it breaks. The boundary conditions for part of that equation are Cauchy conditions. Okay, so TLDR on types of boundaries, we're really not going to do too much, but I'll probably give you a boundary condition with like a boundary value problem with maybe a Neumann on one side, Dirichlet on the other, something like that. To solve it, you literally just do what you need to do to see what needs to happen for the function to be a solution, satisfying the boundary conditions, and then you see if you can find it. It's pretty straightforward. Okay, so here, okay, there we go. For practice problems, see questions 2 through 7 on page 685. And for your meme, here's a SpongeBob meme. Yes, PDEs can be very difficult when you first see them, and this process of separation of variables can be a bit intimidating when you first see it, especially given that we didn't actually finish the problem because, well, again, we don't know how to find t. Well, we can find t, but we don't know how to satisfy the initial conditions. So, yeah, if you have questions there, feel free to ask. It's natural to have questions here. I've pretty much all of my research has involved doing this at some point in time, to one extent or another. So yeah, I've done it a lot. So feel free to ask any questions about the ins and outs, different questions, the scope of it, when you can find these solutions, all that good stuff. Storm Liouville theory. Yeah, that there's a lot of stuff happening here. Okay, so have a good rest of your week, and if you're watching this on Friday, have a wonderful weekend, and I'll talk to you later.